Hello everyone, my name is Gaming Liang. The title of this paper is The Support of MLIR HLS Adapter for LLVM IR. This is the joint work with my advisor Professor Jiankun Li, and we are from National Tsinghua University in Taiwan. This is also the joint effort with our lab members Chen Yuan, Mengxun Yu, and Tailiang Chen and Quanxin Chen who are from University of Twente in Netherlands. This is the outline of this presentation. First of all, we have a brief introduction and technical background. Second, I will talk about the motivation for our work, and then describe the design detail of MHAL and the experiment. I'll briefly introduce some related work and finally give a summary of this presentation. First of all, HLS development status. HLS is becoming more and more mature, and the HLS tools are used in various domains like deep learning, video transcoding, etc. Compared with RTL, HLS can greatly reduce the development time. Most HLS tools are based on single abstraction like LLVM. And then we are talking about MLIR. MLIR uses different IRs at various levels to optimize hardware designs. There are a few projects that are based on MLIR like Scale HLS, Onyx MLIR, Soda OPT, and Circuit. Most of the current HLS tools are based on the old version of LLVM, which is not support for MLIR. Hence, we propose MLIR HLS adapter for LLVM, MHAL, to connect MLIR project and HLS tools. And I'm going to briefly talk about the background of MLIR. MLIR provides different dialects in multiple abstract levels. MLIR provides graph-level representations of various AI frameworks, like Onyx and Torch dialects. One of the important features of MLIR is it allows optimizations considering in or across different levels, which makes it more powerful than LLVM. As you can see, the higher level dialects can parse HLS C, C++, Onyx, PyTorch into MLIR, and then lowering into the lower level dialects and finally into LLVM dialect, which can be translated into LLVM IR. This is our motivation. The current flow of synthesis is writing HLS C, C++ and using tools like Xilinx Vitis HLS to generate RTL. Scale HLS is a new MLIR project which can optimize the MLIR to emit more powerful HLS C, C++ and get better results in synthesis. Ideally, we can generate LLVM IR directly from MLIR to reduce the emission of HLS C, C++ in Scale HLS. But the current HLS tools are based on the old version of LLVM, which is not supported for MLIR. So we propose MHAL address this problem. Now, let's talk about what problems we encountered. On the right-hand side is an LLVM IR, which is generated from MLIR. As you can see, the parameters and the labels are named by number, and this is not allowed for the old version of LLVM. And the second problem is that MLIR can't keep the pragmas information. Pragmas like top function and I/O interface are necessary by HLS tools. It needs to know where the starting point is and how it reads and writes the inputs and outputs. Our adapter, MHAL, uses two LLVM passes to deal with the problems. First, we deal with the naming problem. We use LLVM pass to traverse the whole function and exchanging the initial of the parameters and the basic block labels into an alphabet. As you can see, the left-hand side is the LLVM-IR, which is generated from MLIR. The arguments and the basic block labels are numbers. After adapting by MHAL, we can get the right-hand side code. The initial of arguments and labels are changed into alphabets. Second, we deal with the pragmas problem. Pragmas in LLVM are represented using attributes. As we mentioned, MLIR cannot keep pragmas information into LLVM-IR. With MHAL, we add necessary pragmas into LLVM-IR. As you can see on the right-hand side, at the beginning of the function, vector add, MAXI interfaces are added for each variable. And we also add the top function attribute at the end of IR. And now, we get an IR that is accepted by the old version of LLVM. The main contribution of MHL is translating the higher version of LLVM into the lower version. This also means the LLVM IR generated from MLIR and MHAL can be accepted by HLS tools. There is a problem while using multi-dimension arrays as the function arguments. There are various conversions needed while translating MLIR into LLVM IR, as you can see at the bottom. Convert function to LLVM pass with use bear pointer memref call comp flag will change variables which are stored in memref dialect into the bear pointer. For example, we have a two-dimension array A in C language, and after using MLIR can, we will get argument 0 in memref m multiply m I33 type. Convert memref to LLVM pass will only translate the memref dialect in the body of the function into LLVM dialect. And using convert function to LLVM will change the arguments into a bear pointer in LLVM dialect. This feature works fine in one-dimension array since clan will lower one dimension into a pointer of array. For example, a one-dimension array A will change into an I33 pointer in LLVM-IR, and a two-dimension array B will change into a pointer of an I33 array. This problem can be solved before convert memref to LLVM pass. The reason why we don't solve this after converting memref to LLVM is that the load and store syntaxes before converting memref to LLVM are more similar to LLVM-IR. Look at the codes below. The left-hand side is the MLIR just right before converting memref to LLVM. As you can see, the arg0 is a two-dimensional array and stored it as a shape of 3 multiply 3 I33 array in memref dialect. And the function body also uses load and store operation in memref dialect to operate the value in arg0. First, we change the argument into LLVM dialect with a pointer of I33 array. Second, we change all load and store operations into LLVM dialect. And now, the modified MLIR, just like the right-hand side, can go through the resting conversions and translation. We haven't added this conversion into MHAL, and we keep researching to ensure this conversion can be applied without any error. To compare the results of using HLS-C and LLVM-IR as input to Xilinx VT's HLS, and the influence of different I/O protocols, we prepared 4 types of input. The first 2 types are using same I/O interface, SSD spec array time size. which is the default of Vitis. The HLS-C is denoted as Xilinx default, and the LLVM IR is denoted as Scale HLS MHAL default. The rest two types are using block RAM and MXI I/O interface. The block RAM is denoted as Scale HLS MHAL BRAM, and the MAXI is denoted as Scale HLS MHAL MAXI. Now, let's talk about our experiments. On the left-hand side is a listing of our experimental environments. We use Xilinx Vitis HLS to synthesize both HLS-C, C++, and LLVM, which is generated from Scale HLS and MHAL. And the right-hand side is an overview of our experiments. First, we prepare HLS-C, C++ as the source and use Scale HLS to generate MLIR and LLVM in version 14. Since the LLVM IR cannot be synthesized by Vitis, we use MHAL to generate the older version of IR, and finally generate RTL using Vitis. We prepared three source codes. The first one is vector add, and you can see the source code on the left-hand side. The above table on the right-hand side shows the latency results. As you can see, Xilinx default and Scale HLS MHAL default have the same results since they use the same I/O interface. Using block RAM as the I/O interface also performs the same result in this function. However, using MAXI as the I/O interface performs 1 time higher than others. The below table shows the utilization of these 4 experiments. Similar to the latency, using MAXI as the I/O interface shows the worst utilization, and the other 3 are the same. The second source function is vector multiply. The latency and the utilization are very similar with vector add. Using MAXI as the I/O interface uses about double the cycle as the other 3. However, they are slightly different in utilization. The MAXI interface uses more resource with no surprise, but the block RAM interface uses a slightly more lookup table than the other 2. The final source function we prepared is bubble sort. Again, the MAXI interface performs the worst, but this time, the latency results are over 6 times than other 3. The utilization is very similar to vector multiply. The MAXI interface uses much more resources than others, and the block RAM interface uses a little bit more than the other 2. Let's briefly introduce a few related works. Circuit provides end-to-end flows by developing lots of MLIR dialects to translate into RTL. Onyx MLIR compiles Onyx models and provides 2 dialects focused on standard semantics encoding and the lowering point for Onyx dialect operations respectively. So.opt searches and outlines the kernel's code based on MLIR, and the rest 2 we have already talked about, Scale HLS and Xilinx Vitis HLS. And this page shows the key references of this presentation. Now, I'm going to give a summary of this presentation. MLIR translates the higher version of LLVM into the lower version, which is the current HLS tools like Xilinx Vitis HLS based on. Current HLS tools can profit from the multi-level abstraction of optimizations from MLIR. Compared with directly synthesize the C code, there is no performance loss while translating from C to MLIR to LLVM IR. There are some future works below. First, deal with the multi-dimension array problem that we had talked about. Second, add more pragmas information into LLVM IR. For now, we just put necessary pragmas in it. And then we will keep analyze how pragmas influence the performance and allow users to specify what trade-off they want. Thank you for your listening.